Hi guys! This video is a compressed summary of our third live session on the SoccerNet-v2 challenge. We had the great pleasure to have a presentation given by Silvio Giancola on his action spotting method. Many thanks to all researchers who participated in the discussions and questions.
Feel free to join us for our next session on Thursday, the 13th of May at 1 p.m. UTC. We will have a first talk by Matteo Tomei from the University of Modena on his RMS action spotting method. He is the current #1 on the original SoccerNet. We'll have a second talk by our colleague Meisam regarding our replay grounding benchmark. This will also be your chance to ask questions or discuss ideas. All the links are in the description below. Don't forget to subscribe to this channel to support us, and enjoy!
Today, we have the great pleasure to have a presentation given by Silvio Giancola. You may already know him a bit, of course, but let us first give a few more details about his career.
Silvio grew up in France and studied engineering sciences. In 2012, he got a master's degree in mechatronics engineering at INSA Strasbourg, during which he spent 1 year in Milano, Italy, as an Erasmus student. Afterwards, he went back to Milano to pursue a PhD focusing on 3D computer vision. During his PhD, he spent 6 months at KAUST in Saudi Arabia as a visiting PhD student. In 2017, he received his PhD, and later on, he moved to KAUST to work as postdoc research fellow in computer vision. He is now a research scientist, leading several pieces of research at KAUST.
As you probably know, he published the original SoccerNet paper in 2018, providing the first large-scale soccer video dataset that brings us together today. We've had the chance to collaborate with him for 1.5 years now, and we are proud to partner with Silvio in our SoccerNet-v2 release. Ladies and gentlemen, please welcome Silvio Giancola.
Thanks, Adrien, for this amazing presentation, the amazing introduction. So, well, without any surprise, today I'm going to talk about my latest work on SoccerNet, in particular a paper named Temporally-aware feature pooling. Temporally-aware feature pooling for action spotting in SoccerNet broadcasts. So, in this presentation in particular, actually, I would cover more than just that paper. I will also recall the spotting approach that was introduced in SoccerNet-v1, and in particular, the NetVLAD approach. This new paper is also branded under the name of NetVLAD++, because it's somehow an improvement over the NetVLAD pooling that was introduced during the SoccerNet-v1. So again, this presentation is casual, so at any time, feel free to interact, ask any questions, raise any issue, make a joke, etc., etc. So the outline of my presentation will first be a journey from classification to action spotting. So how that was introduced in SoccerNet-v1. How can we go from clip/Windows classification to action spotting? Then there will be a second part that is basically my work from CV Sports 2018 about the SoccerNet, which is basically an introduction on learning how to pool. And we'll have a third part, which would basically be a temporal-aware pooling, which is this new work that was accepted in CV Sport 21. And finally, we'll get some experiments and some results to show how this temporally-aware pooling is working. But before doing anything, I wanted to have an introduction of the code of that last paper that is already available on GitHub. So I wanted to do so because actually the training of the last networks takes exactly 50 minutes. So it would actually give us the time to go through all the material to collect the results later on. So the code is already available in our SoccerNet-v2 DevKit, okay, under the folder Task 1 Action Spotting, and in a subfolder called Temporally-aware pooling. Aside with the method, the baseline calf that was introduced last year in CVPR, and the pooling method, which is basically the pooling methods that was also introduced with SoccerNet-v2. We have now a new folder called Temporally-aware pooling that is basically this implementation of this NetVLAD++ and beyond. In order to install this, to train and to run that code, you have obviously to create an environment. This environment is handled with Conda. I will be using PyTorch 1.6 and Torch Vision 0.7 and CUDA version 10.1. Obviously, it would work with other version or more recent version of PyTorch, and I believe also some older version of PyTorch and CUDA. Now, the training, and this is what I will launch locally now, is basically very simplistic. We have a main functions that just have one parameters, which is where the SoccerNet path of your data that will be downloaded automatically with the SoccerNet pip package. And how do you want that model to be named? So let's go to that code. This is VS Code. You might be using the same user interface to code your softwares or your project. And this is exactly the SoccerNet DevKit, the task one and the temporally aware pooling approach for action spotting. So I already have created my environment. So everything I need is this in my terminal to activate that specific environment. Go specifically to the folder of temporally aware pooling, which is in task one, temporally aware pooling, and run that line of code that I already modified to fetch my data of SoccerNet that I already have downloaded locally, and created a specific name that is specific for that tutorials, NetVLAD ++ tutorial, which would be that model that we'll be training now. So I'll run that, and I will leave that in the background running. Just for you to know, there are like the code is very similar to what we introduced, what Anthony introduced last week with Calf. We have many different parameters you can actually play with. It's first like pre-computing all the clips, and then you would be able to train, evaluate, and test on specific sets. In particular, I have some parameters that might be novel with respect to the previous code, which are those three parameters, which are the split used for training, the split used for validation, and the split used for testing. As you can see, there is an extra split called challenge that I will not test on that, but at least I will create the output that can be submitted to Eval AI. Okay. So in that specific code, you will see, I mean, it will be training during that presentation. We will collect the results, hopefully in 50 minutes. And the performance of that network should be exactly 53.38. It's extremely reproducible, so mark that down, 53.38. Now let's go back to the explanation of how our code is actually, how this method actually is working. Again, if you have any question at any time, feel free to raise your hands, write something on the chat, or just like unmute yourself, and you will be able to answer all of your questions. Okay. So let's start with our first part of this presentation, which is basically how to go from classification, clip classification, to action spotting. So the method that was introduced in the baseline in the baseline during SoccerNet v1. So during SoccerNet v1, basically you have multiple modules. You have the game, all the frames of the game that are extracted at 2 frames per second. We extract all those the features for all of the frames, either using ResNet.52, C3D, I3D. That was like the original code of it. And we created windows. Okay, so we actually selected a window for that specific game of 1 minute, 50 seconds, 30 seconds. And the idea is that can we pull those features from that specific windows and learn a specific representation for the central frame? Okay, the idea is to take the whole game and split and create multiple windows of, let's say, for the sake of simplicity, of 1 minute, and try to classify and learn a multi-label, multi-class classifier that will classify whether a specific action occur within that windows. Okay, so of course there is many ways of creating those windows. We can make them non-overlapping. We can like the minute from 0 for 1 minute, from 1 minute to 2 minutes, etc., etc. You can make them overlapping. You can do some data augmentation. You can do some hard negative mining. But for the sake of simplicity, we will just consider that those windows are one after the others, non-overlapping. So we will train our model, our multi-label classifiers, and our pooling eventually if there is anything to learn on that regard. And once that is trained, we will take that pooling layer and multi-label classifier, and we will run that in the sliding windows. These sliding windows will create multiple activations that represent the actionness of specific classes in time. Okay, and then by using watershed or non-maximum suppression, we can actually identify the spotting or the localization of specific actions. In this particular case, we're actually tackling action spotting. So we train for the task of classification, and then use the classifier that we trained for the task of action spotting by having a sliding windows in time. Now, to recap a bit, basically, we want to predict the actionness along the time axis per classes. In the specific case of SoccerNet-v2, I was using the ResNet 152 frame features that were reduced using a PCA. I was using NetVLAD with up to 512 clusters and no specific augmentation. Now, how do you go from this actionness to the spots? Well, there were like different methods that were introduced in that specific paper. We had using a watershed of 0.5. So basically you have a threshold at 0.5 and you take whatever is above, that would actually create some segments. Those segments, you can either take the center of this segment or the maximum value in that specific segment. And that is how you actually get your single timestamp that can be used for spotting. Or you can leverage a non-maximum suppression. In that specific version of SoccerNet-v2, I was using still a threshold at 0.5 and then running a non-maximum suppression with a specific window size to only spot the highest value in that specific in those specific windows. So the results are basically you get like multiple activation in time, you get multiple spots, and that specific example that was from the CV Sports 2018 SoccerNet paper, we only had 3 classes: card, substitution, and goal, and it was doing a fairly good, it was providing some fairly good performances. We are all familiar with the metric that was introduced last week. We were able, with a window size of 1 minute, so this bar here, to get multiple mean AP for different tolerance delta. And the area under the curve actually represent the average mean AP that was introduced last week by Anthony. Now, of course, you can use different size of the windows. The windows can be from 5 seconds to 50 seconds. And back in the days, we were actually figuring out that the best performances were performed using center of some segments using watershed with a window, sliding windows of 20 seconds only. And it was reaching 49.7 in particular. So just to summarize that specific approach, that I will go into more details about how to learn that specific pooling, the idea that the journey from classification to action spotting basically start with creating clips. Okay, so some temporal windows in that specific game, learning some pooling approach, either learning how to pool or just pooling using a max pooling and then lifting those features in a higher dimension. Then creating this actionness using a sliding windows for inference and extracting the spotting results using watershed or non-maximum suppression. Now, one of the things that I want to raise here, and in particular in that will be the motivation for the temporally aware pooling, is that consider max pooling. It will be the same thing for NetVLAD. Actually, these pooling approaches are order invariant. This is a very important thing to say, because if I take my windows and I shuffle all the frames, I would get the same exact input. So imagine if you want to spot, for instance, a ball getting out of the field. So basically the temporal information will see a ball that's going out of the field. But if I reshuffle that by basically inverting the time, that ball can actually go inside the field. So you can actually learn some wrong knowledge in that specific case. Okay. So that is basically how to go from classification to action spotting. That will be the basics of how to perform spotting. So now I want to introduce you how can we learn how to pull. And this is the idea of exactly NetVLAD. VLAD and NetVLAD. So first of all, the motivation. The motivation are the following. Basically, in these specific windows where we have multiple frames, we want to pull some meaningful features that will represent the full windows, the full sliding windows that I'm considering into. And by creating and by pulling that in time, you basically want to go from T frames or T features of dimension D to a single feature of dimension D prime. D prime can sometimes be the same dimension of D, but sometimes not, and I will explain you that further. So the most common approaches will be the non-learning approach will be max pool or average pool in the temporal dimension, right? You take the maximum or the average. However, those max pool in those specific example that you can see on the bottom here, they are not necessarily taking into consideration all the set that was introduced in that specific windows. In particular, the max pool will only be defined by that specific point here and that specific sample here, but will discard all the information that is actually taken into consideration here. So average pooling will still like take the overall information of the distribution of the whole set that we're actually pulling from, but yet a single outlier, if we have a single outlier that is very far away, that average will actually be completely shifted and you might learn something different. So that's one of the reasons why NetVLAD was used in video understanding, and in particular in that method named Action VLAD that I may introduce a bit further later, where basically rather than only considering those single stars that represent either the max in the feature space or the average in the feature space of that set, it actually learned to cluster. It create clusters, and it tried to understand if your sets are actually how far away they are from those clusters. Those clusters have a representation, an abstract semantical information that are actually embedded there. Okay. So yeah, this is like Action VLAD that is based on NetVLAD for action for video classification. Now I will just like introduce how NetVLAD works, and starting with his first work called VLAD. So VLAD was introduced in 2010 by this group, Hervé Gégou, and it's in a paper called Aggregating Local Descriptors into a Compact Image Representation. So it was not meant originally for videos, it was meant for image retrieval, okay? So VLAD stands for Vector of Local Aggregated Descriptors. Basically, back in those days, there were like no really like deep learning involved. But the idea was, if I have an image and I extract some sift features out of that, as many as I want, maybe 100, maybe 1,000, how can I find a compact yet descriptive descriptor, a compact descriptors that will allow me to do retrieval or classifying those images into different classes? So VLAD was competing at the time with the state-of-the-art aggregation techniques that you might have learned in your computer vision classes, which was a bag of features, bag of words, or even the Fisher vectors that were very famous for in the literature with facial recognition. Now, how to compute VLAD? How do you define this vector of locally aggregated descriptors? So basically, because you have an aggregation of many local aggregators, you actually have a set. You have a set of specific features that you want to aggregate to put together to learn something from. So VLAD, what it does, rather than taking just the maximum value or the average value, it will learn a code book of K visual words computed with K means. Okay, so rather than just taking the average, you actually cluster, taking the whole data set of what you have available. It will learn those K clusters that are visual words that will describe a vocabulary of those features. Then each local descriptor X, which is one of element of that specific set. So in my temporal windows, this is actually a frame, will be associated with its nearest neighbors cluster, which is basically in that example named CI. And then VLAD will accumulate the residual with the difference between the specific features to the closest clusters. Okay. So this is VLAD that is introduced more formally mathematically with this expression. So this expression is quite important because if you understand this expression, you will understand everything else that comes after that. So formally, you have a set of n d-dimensional features, xi, with I for I to n. So we have n of those features, right? You can understand those xi as the feature of the frame I, okay, at a specific time. And you have t of them, you have actually n of them here. And then given a set of k cluster centers that are defined using the whole data set at your disposal, you are actually learning a feature v, vjk, j being the dimension of the dimension of the features, and k being an index of that specific cluster. And the way it's actually computed is that you have a residual that is defined here as xi minus ck, which is the difference between the feature itself. Like you have a set of 1,000, let's imagine you have a set of 1,000 features. This is your x, you take one of them, and you compute its distance to the closest clusters that was pre-computed originally. You take that distance to the closest, actually you take them all, but you have an assignment, which is a hard assignment for a sample xi to its closest center. So you take the residual of that point xi to all the clusters, but then only consider the residual for the closest clusters. All the others are actually equal to 0. You do not take them into consideration. Now, the vector VLAD is defined as the sum over all the sample n to this assignment. So it basically is a binary information, 1 if ck is the closest centers or 0 otherwise, of the residual of a specific sample to the center of this cluster. Again, those clusters have some abstract semantic information embedded here. Okay. So this is how you define VLAD. So practically, how does that look like? Okay, like how does that look like? It's actually great to introduce this mathematical formulation, but what are we exactly trying to do? So basically, if you have an example here of blue circles and X, so blue circle will represent, for instance, an image of a dog, and the crosses will represent the sift features of a cat, for instance. This is the feature space, and you plot those specific features in that specific set. You put them into that feature space. You learn some clusters, and you might be familiar with the Voronoi representation of the cluster. So this polygon here is a Voronoi representation of the multiple clustered with which center one is here, the other one might be here, the other one may be here, the other one might be here, etc., etc. And what you're trying to do is, like, for each of those clusters, you will learn, for the representation of the dogs here, for instance, how far away you are from the center cluster. Okay, so how different you are from the average cluster, actually. So how does that work? Practically, the samples are assigned to the clusters. So in that specific cluster, I assigned all those blue dots. They may have some blue dots, some blue circle here, some blue circles there, but we only consider the one that is in that specific cluster that was hardly assigned to that specific cluster. We average the residual of the clusters. This blue arrow will actually represent the average displacement of the center with all the sample of that set. And then you have a couple of normalization per cluster and over all those features. And what you end up with is actually k features of dimension d. Okay, so the original inputs are a set of n features of dimension d. This is here the input n times d, and the output is actually k features that each of these features are of dimension d and represent how far away you are from those clusters. Okay, so that is how VLAD was introduced. Also, in that specific paper, it was actually slightly improved, and it was this concept of normalization in all about VLAD from Andrew Zisserman during CVPR 2013. Now, this was about VLAD. So the idea is that it's some very descriptive representation that is better than a simple max pooling or an average pooling that is more expressive. So the concept is that it is more expressive because you consider different cluster inside your set. You don't just consider average pooling or max pooling. Okay. Now, one of the problems of this NetVLAD for deep learning is that this specific assignment that has been assigned during this VLAD approach is a hard assignment. It is not differentiable. Okay, so this A that you can see here is either 1 if CK is the closest centers or 0 otherwise. And for that reason, actually this assignment is not differentiable. So how to make that differentiable? In the paper NetVLAD, that is a paper from 2016, CVPR, they define a soft assignment for each of the sample xi to the center cluster xk. And this soft assignment is based on the distance between your point xi and and all the center ck. Okay, so actually here they are creating a soft mean of the distances. So you want, for instance, in that specific cluster, for that specific points, for instance, it will be the closest will be from that specific cluster, but that specific point is also the second closest will be here, the third closest is here. So rather than actually assigning one that specific sample to that specific cluster, it might set 0.8, for instance, but it will still assign it 0.1 or wait to 0.1 here, maybe 0.001 there to that specific assignment. So basically, soft assignment is a way to have an assignment that still goes from 0 to 1, but in a soft fashion. And the softness of this assignment is defined by that alpha parameters. Okay, so that's the main idea of how to make VLAD differentiable through this NetVLAD, and that is exactly how NetVLAD is defined. So NetVLAD is a differentiable VLAD that is more expressive, of course, again, than a max pool over a set or an average pooling over the set by using this consideration of multiple clusters here and there. Now, how NetVLAD formalize that specific module, it's a layer at the end, is that they take that specific formulation that you have here and they define WK, a matrix WK, where 2 alpha CK and BK, that is basically this minus alpha CK2. And if you plug that into here, basically you can simplify this square by splitting the different term of that specific term into a WK and a BK. That, guess what, is just a set of weights and some bias. Here there is a specific trick that if you want to look at the math, basically what's happened in the softmax between the different clusters is that alpha xi to the square will cancel from the numerators and the denominator. So you end up with that specific formulation for that soft assignment. That is nothing else than taking your features xi, learning a linear layers with WK and B, and then applying a softmax between those values. Okay, so by doing that, you actually have an assignment that is differentiable. It goes from 0 to 1, and basically this assignment to the closest clusters that you will use to represent your set. All right, so that being defined, you actually have one layer like this that you can plug and play directly to any network. Okay, so you can define a NetVLAD layer that is basically that thing. So this is the assignment that I just defined before. This is the residual to the closest center, and you actually have as an input n times d local descriptors. So you have a set, okay, a set of n SIFT features or n frame in a Windows, for instance, that are all of dimension d. And what you do is convolutions, where you learn W and the B for that specific point X. You take a softmax out of those lifted features. This is the soft assignment that is defined here. And then you aggregate this alpha, this assignment with the residual xi minus ck in this, what they call VLAD core. And then you have a bunch of normalization, nothing fancy, just to make that works. So as I said before, the input is actually n times d. So it's a set of n features of dimension d. And the output is a set of k features of dimension d that are descriptive of those multiple stars that I showed you before. So in practice, just one small detail. So technically WK and BK are function of C, but for the sake of learning, there is more details in that specific paper. WK, BK, and CK are actually learned independently. This is like a small minor, it's a minor trick, but actually it somehow breaks a little bit this insight that was brought in with VLAD. And actually this concept of cluster might not be exactly what's happening here because you are breaking that dependency of them. Anyway, that being said, I do believe NetVLAD is very powerful, and actually there is like some link of for NetVLAD with transformers. So this is just like a parenthesis I wanted to make here. So if you are very familiar with those transformers, and in particular the multi-head attention, the multiple head attention also use a softmax to some residual, but the softmax is not across the heads or those different clusters. You don't like have a softmax for assignment or for each single clusters, but you have that across the sets. So it's quite interesting, and if you want to investigate that further, and since transformers are quite hype in the literature, there is some links between NetVLAD and transformers. So have a look at that if you want to. Now, to summarize and to go back to the application of videos, how was this NetVLAD applied? Originally, it was applied for this during the CVPR paper, CVPR 17, this Action VLAD. Action VLAD was for video classification. It has an input of RGB and flow, but let's forget about the flow so far. The single RGB actually explained that concept. And the idea is that they want to use a NetVLAD aggregation between all the frames of that video. So you have multiple videos of different lengths, sometimes 10 frames, sometimes 1,000 frames. With this NetVLAD approach, they were able to learn some descriptors of dimension k times d that will represent actually some semantically meaningful cluster. So for instance, if you want to classify that as a basketball shot, what you actually having is that maybe some of the features would actually gather around a hoop, dribbling. You might have the concept of jumping in the flow realm, group, or the ball, etc., etc. So rather than just like pulling everything into a single feature, you have k of them. Okay, with this idea.
Silvio, we cannot hear you anymore.
Can you hear me? Test to test.
I can hear Silvio.
I can hear too.
You can? Okay. So
yeah,
I think it's only
now it's good.
Getting back.
Okay. Yeah. Sorry about that. Okay. So just to close that, basically the idea of NetVLAD is that you can learn a vocabulary of concepts, and each single cluster that we were learning before, that you CK, we're actually considering to one semantic word that you will automatically extract in a clustering fashion. For the sake of understanding what's happening in a set of features, okay? And again, in that specific paper, Action VLAD was better than non-learnable pooling layers. If you would only consider like from some metric, I don't remember what that metric means, but if you consider only average pooling or max pooling, you get less performances than when you consider this concept of Action VLAD that are more expressive. That are more expressive into the sets that you are pulling from. Okay. So the same concept is applied in the baseline that we introduced in SoccerNet-v2, but instead of considering the whole video, now we are considering again that specific window. So we have a windows with n frames that are all that the feature are all extracted, and the idea is that all frames will contribute not for a single cluster, but for all those different clusters around. So you will have maybe like here you have where is that? Here you have a close-up camera. Maybe you will have this frame will actually project here, and it will tell you like some residual with respect to all the close-up cameras. Or maybe here in the concept of running, you might have different type of running that will be learned somehow, or for shooting, or etc., etc. Okay, let's proceed then. Hopefully actually my network will be trained by that time. That will be amazing. So how do we go from learning how to pool, and what is this temporally aware pooling now? So as I mentioned before, basically to go from clip classification to action spotting, what you do is that you consider like clips, which are temporal windows. You have a pooling approach that pool among that specific windows, either learnable or non-learnable. You consider that actionness with these sliding windows, and you extract from which you extract the spotting using watershed or non-maximum suppression. Now, one important thing that I was mentioning before is that pooling are order invariant. What does that mean is that if I take again my temporal context, if I shuffle everything, well, I will get the same exact features. And that is not necessarily something that I want. Okay, it's not necessarily something that I want, because actually in CALF, in the paper RMSNet, it has been shown that the context before and after carry on different semantic information that can be leveraged. So the whole idea of this NetVLAD++ is the following: can I split the cluster, the vocabulary that I'm learning, rather than having one big vocabulary for the whole temporal context of maybe before, I don't know if you've seen, but it was 10 different concepts, such as goalkeeper, cheering, shooting. Can I split half of those clusters to belong for the future temporal context and half of those clusters for the past temporal context? So maybe they will learn some specific information that will be exactly about the past temporal and the future. Take an example, for instance, for a goal. The past context can be shared between a simple shot, for instance. But if having a specific temporal context, future temporal context, that is exactly about having some crowd excitement, some replay, some cheering, etc., some slow motion or replay, that would actually be very indicative. So it's basically injecting a temporal prior for my set. I have a big set from this temporal context, and I have a prior saying that something happened before, something happened after, and those are different contexts that does not necessarily needs to be merged together. So basically what I'm doing here in this NetVLAD++ is that I'm injecting the prior of saying that the vocabulary of what you learned before and the vocabulary of what you learned after that is different. Now, for sake of, well, I will go through that later. For sake of not increasing the complexity and the number of parameters that you want to involve there, you don't have the same amount of vocabulary for each single subset, but you actually use half of your capacity for the past temporal context and half of them for the future temporal context. Now that actually NetVLAD is very clear to you, basically what is actually doing with NetVLAD++ is you create two NetVLAD features using for all of them half the number of clusters and half the temporal side. And you get two NetVLAD features, VB and VA, as V before the actions and V after the actions. And you just aggregate that by just concatenating the two features that you have. So rather than having one single K times D, what you'll have is it's actually written here. So to actually have the equivalent number of clusters and hence the same number of parameters, you will define your number of clusters for after and before as half the number of complete cluster that you have. And you also have an equivalent temporal context, TA and TB. Of course, one could actually play with those hyperparameters, maybe focusing a higher vocabulary of what happens after or before, also having different temporal context after and before. I have not played with that, and I fixed them to be T equal T/2 and K/2. So that's it. That's how NetVLAD++ actually works. It's once you actually understood like how NetVLAD work, that method is nothing else than just splitting the temporal context before and after. So, okay, once you understand this temporally-aware pooling, you see like, well, it's pretty stupid, right? So let's look at the experiments and how does that look for the experiment. So first of all, I tried in this specific code, you have the possibility of running this baseline of max pool. Max pool was using ResNet 152, was using a PCA, it was pooling with a max pool, and then was using NMS at 0.5. This NMS at 0.5 is actually an underestimation of the performances because you're actually discarding everything that has a score below of 0.5. So in the final matrix of average mean AP, it might look slower. And there is a specific comment on the website about that, on the development kit about that. Another baseline I played with is the NetVLAD, is the same one again from SoccerNet, ResNet 152, PCA reduced, NetVLAD for the pooling, and again NMS at 0.5, which again is not optimal. You can fairly improve this NMS and final performances. Now the new NetVLAD++ has this new modality of pooling. This is temporally aware, but that is not the only modification I did on that specific layer. There is, of course, the NMS that was optimized on that specific case. It's not threshold anymore at 0.5, which was producing like was under-reporting the performances. And I was using as a dimensionality reduction. I'm not using PCA anymore, but I'm learning that specific dimensional reduction. So as you might know, just to have maybe, I don't know if I have a few explanations for that, the ResNet features have a dimension of 2048. And the PCA was used over the training, validation, I think, maybe testing as well in unsupervised fashion using principal component analysis that was basically reducing, it was learning a matrix that will reduce the features from dimension of 2048 to 512 by keeping the principal components. Now, this PCA is great if you already have those features, but they need to be estimated offline. And they have one constraint, which is actually the orthogonality of the new dimension. So basically what happened is that you are learning somehow a rotation, and that specific that specific matrix you're learning will enforce orthogonality in the new space with respect to the first one. So by reducing this, by removing this PCA and using a linear layer, you can actually learn any linear combination of the previous features. That might lead to better performances at the end, and is the case that I'm also showing in the paper. Now, it's not the main contribution, to be honest. It's just reducing a PCA with a linear layer, but it shows that fine-tuning those features actually improve the results a lot. Now, to go back to the results, you might be familiar with this table if you're working with SoccerNet-v2. This table was from SoccerNet-v2 paper, from which I reported the performances of this NetVLAD++. So MaxPool and NetVLAD come from the SoccerNet paper. AudioVid was an improvement on top of NetVLAD that also considered audio features. And CALF was the CVPR paper from 2021 with Anthony and Adrien as well. NetVLAD++ performed 53.4. This is the max performances over 5 run, okay, 53.4 that I reached. And there is like a consistent improvement over all the different baseline at the difference of the goal that actually CALF outperformed by 0.6 point. So it means that maybe there is CALF is still the best for goal detection, goal spotting, sorry. Further ablations, or how to reach that specific performance of 53.4. This is the best over 5. Here I'm reporting like the average over those five results. So the further ablation is first of all by selecting the best NMS, window size, and not having this threshold at 0.5, and also having the best temporal windows I'm using for the sliding windows and to train. We can actually reach 48.4, which is fairly high. Now, NetVLAD++ reached 53.3, and if you remove the temporally aware concept, you actually lose 3.1 points, and the linear layers also contribute 2.6 points. And those are a different version to reach at the final performances that are here. If we consider those per class, what's interesting is actually that the temporally aware performances works somehow better to some extent for some classes such as goal. So it looks like having some temporal features, you actually get like a plus 5% in the goals, in the penalty as well. You get impressive performances also in the individual free kick and the fall as well. Maybe the fall is that because when you have a fall, what's happened is that you have some context before and after that are completely different. So by disentangling those two vocabularies and learning something for before and for after, you might learn something more meaningful for all of these subsets. Same thing with throw-in, that was a massive improvement, and ball out with respect. I'm just comparing this temporally aware business. This is the ablation I was mentioning before about the temporal context, having a sliding windows. I think Kanav was asking if you increase T, will you get like an improvement? Actually, I figured out that T equal 15 seconds was the best performance I could get. This is with K equals 64. If you increase the number of, so actually K equals 64 means I'm using 32 after and 32 before. But if you increase that vocabulary, you might actually try out with higher window size. This is what I was mentioning about the memory consumptions. This is the number of cluster K, and with the performances average and min max. So it looks like, of course, the higher number of K, the better the performances. But really, what you see is a exponentially increasing number of parameters. So in practice, I stopped that at 64. Again, an ablation of the video encoders. It looks like that concept works on also using I3D and C3D. You get an improvement even using simply the PCA reductions with the temporally aware, and also using these linear layers for the PCA, you get a second improvement, significant for all of them. Another interesting approach is that this temporally aware works not only with NetVLAD, but it also worked with NetRVLAD, which is a variant of NetVLAD that does not consider the residual. It's just like, it's not that important. But what's really nice is actually the average pooling and the max pooling. Once you have a temporally aware, and especially the average pooling, if you are temporally aware, you already reach 40.6 plus minus 0.2, which is like fairly good results, to be honest, when we know that I think in SoccerNet-v2, we got like a state of the art was around 43, more or less. And here you don't have to learn any parameters, actually, in this average pooling. You just pool before and after those features. And then you concatenate those, and you just have a linear layers that goes from the dimension, 2 times the dimension of the features to the final classifier. So we are talking about 512 or 512 for the after and the before, and 17 classes, which is actually 17,000 parameters. So fairly low amount of parameters to learn on top of that. And this is at the time of the submission, the performances of the challenge. So here on the challenge, this is the performances that are reported on Eval AI that are publicly available. This is NetVLAD. CAF was reaching 42.2. RMS actually, at that time of the submission, was reaching 49.66 when I submitted that paper. And NetVLAD plus was reaching 52.54. Now, the way I was getting these performances on the challenge is that because it's the challenge, you can actually train and evaluate on whatever you want, right? But not on the challenge set. So in that specific example, I was training on the training set and the validation set, and I was validating on the testing set. So I was like just shuffling the data, which is a fair assumption to do for your submission that you are doing for the challenge, as soon as, of course, you don't use the challenge to evaluate from or to train from. And this is how I get those performances. Of course, those performances are now outdated. There is this visual analysis of human that got 55.0, and AI Image Lab RMS that got 58.73. And as we said last week, there is like some method actually went over 60. So basically, the take-home message is what's of that specific submission was first of all, we improved the hyperparameters for NetVLAD. We have a better performances with a better NMS and a better temporal windows. We introduced a learnable dimensional reduction that's boosted a little bit the performances, which brings the concept of fine-tuning the features for the scope of soccer would actually be great. We introduced a temporally aware pooling. We got some great results. It trains in 1 hour. So actually, I will go back to my training and see what type of results I get. But just before that, just a few contexts about what's going next. What's next, I guess, that are interesting direction for research would be: can we consider a larger context? Can we have end-to-end training, like from the video to the end task, not only considering the features extracted with ResNet, for instance? And I think RMSNet was actually able to do so. And maybe we can consider transformers. NetVLAD is one type of aggregation, transformer is another. Maybe it would be interesting to investigate that. That's it. So maybe before anything, I will look at my code. Okay, so it was training for 81 epoch, actually 83, then it stopped. Then it was testing for the spotting, and it was evaluating at the end of the spotting, and the average min AP visible for all the data was actually, as I mentioned before, 53.38. You have the results per class and per visible, non-visible, and it also extracts automatically the performance. It inferred the results for the challenge set, and directly in the code you might want to look at that. This is the output they have. I have a zip file that includes the test, the result for the test set, and the result for the challenge. So you can directly take that zip and submit that to your to Eval AI, and you will get your result there. That's it. Thank you for your attention.
So then thank you very much, everyone. And thank you, Silvio, of course. We will have our next live session next week, which will be Thursday, same time. So Meisam will present the replay grounding with the code and the baselines. And we will have also Matteo Tomei, who will present RMS, his method that is now first on SoccerNet-v2. So thank you in advance for that, and we will tell you the details, of course, on Discord as usual. All right, thank you. Bye.
Thanks, everyone.
Bye.
Thanks for listening, and if you have any questions, feel free to reach out.